All right, I'm glad you're here for this slice of physics. I'm going to tell you a little bit of a story in this video of what light is about, and we'll look at some properties of light. So in this course, we started our discussion talking about charges, their properties, how they interacted with each other through forces, which led us to this concept of electric field. And then that kept us busy for several weeks talking about potential and potential energy and circuits and currents and all that, which finally led us to the magnetic properties of current. And that got us into magnetic fields, which brought us full circle back to changes in magnetic fields resulted in a current. So there is a close relationship between electric fields and magnetic fields. So this word here puts those two things together. So we're going to talk about properties of electromagnetic waves. So these waves have electric and magnetic properties. And we'll start with Maxwell's Leap, where he figured out that light is nothing but an electromagnetic wave. It is a transverse wave, so it has a wavelength and frequency. And Maxwell figured out that light was an electromagnetic wave with oscillating electric and magnetic fields. And an interesting property of it is it does not need wires, it does not need any medium, it can propagate in vacuum, and it goes in vacuum at a constant speed across all wavelengths and frequencies. That'll then lead us to talking about the electromagnetic spectrum, where we look at all kinds of light waves from gamma rays to radio waves. And we'll talk also about the particle nature of light, which the fundamental particle of light is called a photon, and we'll discuss what its energy is, and wrap up talking about how the intensity of light drops off with distance from the source that's emitting the light. All right, so let's talk about Maxwell's Leap. Every 100 years or so, there's a scientist who has a fundamental revelation, and Maxwell came up with the revelation that light is an electromagnetic wave. And that led to a lot of very interesting consequences. So what Maxwell figured out was that he realized that in a three-dimensional setting, where I have X, Y, and Z axis over here, he figured out that the electric field oscillates along a certain axis, while at the same time, the magnetic field oscillates along this horizontal axis. And as a result of those two oscillations, the light wave itself propagates along the third axis with a speed. So in this case, this was the electric field oscillation. Here was the magnetic field oscillation, and that resulted in the propagation of light. So this realization categorized an electromagnetic wave as light, and some of its properties were that it's a transverse wave. What we mean by transverse wave is that the oscillations that are responsible for the propagation of wave are perpendicular to the direction of propagation. So in this case, the propagation is along this x-axis. The electric field oscillation is along the y-axis, and the magnetic field oscillation is along the z-axis. So both the electric field and the magnetic field are oscillating in a direction that's perpendicular to the propagation of the wave, and that's what makes it a transverse wave. In a longitudinal wave like sound wave, which is a pressure wave, you got high pressure areas and then lower pressure areas. And in this case, the particles that are responsible for the wave propagation are oscillating along the direction in which the wave is propagating. So they're parallel to it. So light is a transverse wave. So let's talk about some of the fundamental properties of transverse waves. So I'm just going to take the two-dimensional version here, and here's how a wave looks. It's like a sinusoidal function, sine or cosine function. And the two fundamental properties we're going to talk about now are wavelength and frequency. So wavelength is literally the distance. So it's a linear measurement. It's related to space. So wavelength is the distance you can think of as between two consecutive crests or two consecutive troughs. So if I were to continue this over here, this trough to this trough will also be wavelength. Or I can take any point in the wave. So let me take this point and I go to the next point. So when I get here, I haven't gotten to the same point because the point I started with, the wave was going down. Now I'm touching the wave, but here the wave is going up, so I haven't completed one full cycle. I need to keep going till I get here. So this will give me the wavelength. So lambda here is wavelength, and in SI units, it'll be measured in meters. So that's along the wave. But if I see a temporal view of this or a time view of this, over time this wave will change and this particle here will bounce up and down. So a little bit later the wave might look like this. So as the wave changes with time, there is a time measurement to it, and that is given as frequency. F is written as frequency, and this is the number of times let's call this a particle, even though we're talking about electromagnetic waves which don't need particles. In that case, it'll be the oscillation of the electric field or the magnetic field. But if we think of it as a water wave and you have a leaf that's sitting here bobbing up and down with time, it'll be the number of times a particle bobs up and down per second. So this is the number of oscillations per second. You'll remember from Physics 1, the previous class, that we talked about period or time period. And for a wave or an oscillation, that was the time it took to complete one full cycle. And you'll remember that we talked about it at that time to say that a frequency is simply 1 over t. So it's 1 over how long it takes to make one full oscillation. And so the measurement of this in SI units will be 1 over second, which is called hertz. There can be other units like RPM, which would be revolutions per minute, or oscillations per minute. Or you could say RPS, revolutions or rotations or oscillations per second, which is the same as the hertz. All right, back to our discussion about light. Light is an electromagnetic wave, and it's an oscillation of both electric fields and magnetic fields. So the changing magnetic field produces an electric field, and the changing electric field keeps that magnetic field changing. So these two oscillations can self-propagate each other and have the light wave moving through vacuum. You do not need any matter for light to travel in. And Maxwell showed that, remember we said the force on a particle from the electric field is Q times E, and for equilibrium that had to be equal to the magnetic force, Q times V times B. The Q's canceled, and we got this relationship of E equals VB. Well, for light, it'll just become E equals CB. C is the speed of light. Oh, by the way, there is also a relationship between the speed and wavelength and frequency. For any wave, the speed of a wave equals the wavelength times the frequency. And wavelength is measured in meters, frequency is measured in 1 over second. So the unit of this becomes meters per second, which makes sense for speed. So speed of any wave is given by this. And since I like to run, I think of this in the terms of running as I've got a speed with which I run, and that's a multiplication of the wavelength. So for running, wavelength is equal to the stride length, how long my stride is, and the frequency is measured as cadence, how fast my feet turn while they hit the road. And if I want to go faster, I can either increase my frequency, turn my feet faster, or increase my stride length, open up my stride. Either of those things or both of those things will help me go faster as a runner. Well, when we're talking about electromagnetic wave, there is a very special property. So Maxwell, when he figured all this out, he also figured out that the speed of light is nothing but 1 over the square root of mu naught times epsilon naught. You have seen mu naught, which is the constant we use when we work with magnetic fields, the permeability of empty space. You've seen epsilon naught, which is the constant we worked with when we were talking about electric fields. And Maxwell derived this relationship that the speed of light is simply this, 1 over square root of mu naught times epsilon naught. Now this tells us something very special. This tells us that the speed of light must be a constant. It cannot vary with anything. So even though light comes in lots of different wavelengths and frequencies, the speed of it in vacuum, by the way, this equation only works when light is propagating in vacuum. So C is the speed of light in vacuum, and it's a constant. And so for light, I will write C equals lambda F, and that's a constant. So I cannot, if I'm light, I can't go faster, I can't go slower, I can increase my frequency and increase speed as a result. So because C is a constant, increase in frequency results in decrease in wavelength that corresponds to it, and a decrease in frequency corresponds to a wavelength increase, such that the product of the two will always be a constant. And I can rearrange these terms to get lambda equals c over f, or f equals c over lambda, and c is going to be a constant no matter what the wavelength or frequency is. All right, let me clear up some room and continue this discussion. So we said c is lambda times f is a constant, and Maxwell figured out that that was 3 times 10 to the 8 meters per second, 300 million meters per second, or 300,000 kilometers per second, or 186,000 miles per second. So it's pretty fast. Light can go around the Earth 7 times in a second. It can go from the Earth to the moon in about a second, but it's still a limited speed, and it's a constant speed in vacuum. And by the way, we knew the speed of light for hundreds of years before Maxwell calculated it using the theoretical equations that he came up with, and that's what gave him the insight that an electromagnetic wave is nothing but light. Now, one important thing here is, as we have just said, it is constant across all lambda and f. So we will see shortly that light comes in many flavors based on changing wavelength or frequency, but they all travel at the same time. One cannot travel faster or slower than the other. But please don't confuse that with the speed of light being constant across all mediums. The speed of light is not constant across all medium. So when you send light through glass or water or diamond, you can slow it down. When light is traveling inside stars where there's a very dense plasma, light actually slows down a lot in those mediums. So it's not constant across all mediums, but the important fact is that it is constant across all wavelengths and frequencies, which makes light unique. No other wave is like that, but light is. Okay, with this in mind, let's talk about the electromagnetic spectrum. So now we're talking about the flavors of light as wavelength changes. So on the left here, I'm going to have low frequency, and on the right, I'm going to have high frequency. And we categorize it as R, I, V, U, X, and G. So you guys have seen this before in some other class, I'm sure. So this is radio, this is infrared, this is visible light, this is ultraviolet, this is X-rays, and gamma rays. Those are the different flavors of light that we talk about. And by the way, the frequency goes from close to 0 to infinity by the time we get to gamma rays. So similarly, the wavelength also ranges from 0 to infinity. 0 is the theoretical limit. We're not going to have something exactly at 0, but we could have a wavelength that is, let's say, 10 to the power of minus 10 meters or 10 to the power of minus 100 meters, as close to 0 as you want. So we see that frequency increases as we go from radio to gamma rays. Gamma rays have the highest frequency, and radio waves have the lowest frequency. Wavelength, on the other hand, increases the other way around. Radio waves have the highest wavelength, and gamma rays have the lowest wavelength. You remember that the product of the two is a constant. Lambda times f is c. C is a constant. So as lambda goes up, frequency has to go down, so they have to go in reverse directions. The speed of light, which is equal to the product of the two, is a constant. It doesn't increase one way or another. Radio waves travel exactly at the same speed as infrared waves, as visible waves, ultraviolet, gamma rays, or X-rays. It doesn't matter which flavor it is. They're all traveling at the same speed. And to give you some feel for what the wavelength values are, I'm going to give you some values here for these different types. So radio waves start about at a millimeter and go beyond that. So a 1 meter long electromagnetic wave will also be a radio wave. 100 meters long electromagnetic wave will also be a radio wave. So radio waves go up to infinite wavelength, and they start about at a millimeter. And when you talk about infrared waves, you're generally in the micrometer regime. So 1 micrometer on up to about 100 micrometers or something will be the infrared. Visible is a very small portion of the spectrum, and that varies from about 0.7 micrometers to 0.4 micrometers. And by the time we come to the border between ultraviolet and X-rays, we're getting to about a 10 nanometer range. X-rays will be about 1 nanometer range. And then an angstrom, which is 0.1 nanometers, is also in the X-ray range. And that would be the size of a hydrogen atom, if you will. So the wavelength of light that is equal to the size of a hydrogen atom will be an X-ray flavor. And gamma rays will be wavelengths that are much smaller than that even. All right, one last thing while we're talking about the electromagnetic spectrum. This very unimportant small portion of the electromagnetic spectrum that we call visible, we give it a lot of importance, and that's because that's what our eyes can see. So we take that little sliver down and break it into the different colors. So here we've got red on the longest end of the spectrum to orange, yellow, green, blue, indigo, violet. Violet is at the end where you got the smallest wavelength or highest frequency. Red is at the end where you got the highest wavelength or smallest frequency. So these are our rainbow colors, and they are further definition of this visible part of the spectrum. All right, let's take an example to kind of bring this home. I just told you that the visible part of the spectrum varies from 0.4 micrometer to about 0.7 micrometer. So red will be here, the longest wavelength, and blue or violet will be at the other end. So I'm going to take 0.5 micrometers as my example. So let's say there's a flavor of light that's kind of in the green range, where the wavelength is known to be 0.5 micrometers. By the way, 0.5 micrometers is the same as 500 nanometers or 5,000 angstrom. They're all the same thing. You know what a nanometer is. It's 10 to the negative 9 meters. Micrometer is 10 to the negative 6 meters. Angstrom is a unit you may have not seen before. 1 angstrom is equal to 10 to the power of minus 10 meters. And that's roughly the size of a hydrogen atom, the diameter of it. So if I want to know the frequency of this green part of the visible spectrum, somewhere in the middle of the visible spectrum, what the frequency is, I can calculate it. So I've got C equals lambda F. Rearranging that gives me F equals C over lambda. I know C is 3 times 10 to the 8 meters per second. I have wavelength as 500 times 10 to the negative 9 meters, 500 nanometers. And so when I calculate this, I will get 6 times 10 to the 14 hertz. So very high frequency. So these little electric and magnetic fields are oscillating that many times per second, but their wavelength is only half a micrometer, which is about 1/100 the width of a typical strand of human hair. So very small wavelength, very high frequency, gives it a pretty high speed. All right, so far we've been talking about light as an electromagnetic wave. But one other thing I want to mention is that light also exhibits particle-like properties. It turns out that nature at its most fundamental level is very mysterious. So light can be a wave, light can be a particle, depends on which experiment you're doing, that it shows one property or another. And when we talk about these bundles of light, we talk about a particle of light. We've given it a name called a photon. And you can't have light come in half a photon or 1.5 photons or 2.75 photons. It can only come in integer multiples of photons. And the energy of a photon is given by H times F. H is called Planck's constant. Planck is the scientist that did a lot of this work early on and figured out these relationships. He was also a mentor and supporter of Einstein, who figured out a lot of other special things about light. And this Planck's constant is a universal constant, and the value is 6.63 times 10 to the negative 34 joule second. So the photon that we just worked with in the middle of the visible spectrum, which had a frequency of 6 times 10 to the 14 hertz, we can now figure out what its energy is going to be. So this would be 6.63 times 10 to the negative 34 times 6 times 10 to the 14 hertz. So this will give me a value of 3.98 times 10 to the negative 19 joules. If I take joules seconds and multiply it by 1 over second, the seconds will cancel and I'll get energy in joules, which is great. That is the SI unit of energy. And since that's such a small number, in order to make sense of it, I'm going to convert it to electron volts. You guys will remember we used electron volts earlier in this course, where we said 1 electron volt is 1.6 times 10 to the negative 19 joules. So then I can convert this to electron volts by dividing by 1.6 times 10 to the negative 19 joules multiplied by 1 electron volt. So this is what I'm multiplying by, this factor here, which is 1. and this gives me a value of 2.49 electron volts. So one little photon of visible light of 500 nanometer wavelength will contain an energy of 2.49 electron volts. All right, the last topic I want to talk about is how the intensity of light diminishes in a given area as we go farther from the source. So if I have a light bulb here that's emitting light, and if I'm 1 meter distance from it or 2 meters distance from it, the intensity of light diminishes. And the way it diminishes is so let's say this light is spreading out as it goes out from the source. So here it fills a square of this size, but by the time it goes twice the distance, that same amount of light will now fill a square which has twice the length and twice the width as the previous square. So this the size was x, the area of that is x squared. Here each side, just based on simple geometry, you can see will become 2x, and so the same amount of light will be contained in 2x times 2x or 4x squared area. So if I take a patch of one size of light there and the same patch here, and I want to see the intensity will drop off as the square of the distance. So the intensity at a distance from the source will be given as the power of the source divided by 4 pi r squared, where r is the distance from that source. This is similar to lots of other relationships you've seen in this course where things drop off as the inverse square of the distance, so does the intensity of light. So we'll call this an inverse square relationship. So one quick example on this, and we'll end this video. If you have the sun in our solar system over here, we got the Earth. Earth is at a distance of 1 AU from the sun. And then you go out from Earth to Mars and then Jupiter. Jupiter is the biggest planet in our solar system. The distance of Jupiter from the sun is 5 AU, 5.2 AU, but let's just take 5 AU and just one significant digit. So whatever light we get at the Earth, if we want to see what Jupiter gets, because of the inverse square relationship, because the distance is 5 times, Jupiter's light ratio compared to the Earth will be 1 over 5 squared, or 1/25th the amount of light that the Earth gets, which is about 4%. So if you lived at the distance Jupiter does, you will be very, very cold, because even on the sunniest day, you're only going to get 4% of the light that we get here on Earth. All right. So in this video, we've discussed the properties of electromagnetic waves. We talked about how Maxwell figured out that it's a transverse wave of oscillating electric and magnetic fields. So it has a wavelength and a frequency, and frequency is nothing but 1 over t, where t is the period of that oscillation. And because the electric fields and magnetic fields are related based on the equilibrium equation, we get this relationship between the electric field and magnetic field at any point in a light propagation. And we also noted that light travels at the same speed across all wavelength and frequency in vacuum. And in vacuum, that's 3 times 10 to the 8 meters per second. And that's the product of wavelength and frequency. Then we looked at the electromagnetic spectrum, all the way from radio waves to gamma rays. And then we dissected this one visible part into all these colors, going from red, orange, yellow, green, blue, indigo, and violet. We talked about a bundle or a photon of light, which had the energy of hf or hc over lambda. And lastly, we saw that the intensity drops off in accordance with the inverse square law. Thank you.